Chapter 7 moves us into our fourth and final unit for our trig course, and we start talking about applying trig, and we're going to move into vectors. Vectors is something that you see a lot of in physics, not as much up to this point in math. We're going to be working with oblique triangles. Most of our trig to this point has been focused on right triangle trigonometry so that we have a hypotenuse. When I have an oblique triangle, it is not a right triangle. There is no hypotenuse, so we can't use the Pythagorean theorem to help us out in solving. We have other methods to help us out to solve. One way is to talk about congruency, to find different congruency statements, and there are three different congruency axioms that we are going to learn and work with as we work with oblique triangles. The first one is side angle side. If we know two sides and the included angle of any one triangle, and we know that they are equal respectively to the paired two sides and the included angle of a second triangle, then we know that those two triangles are congruent. Well, congruent, this is my symbol for congruent, and congruent literally means they are the same size and the same shape. Both, same size and same shape. Side angle side, this order is super important. If I'm looking at a triangle and I am looking at side angle side, I'm talking about two sides, one side, two sides, and the included angle. So if I'm talking about these two sides, I have to know this angle. That is the angle that is included or is formed by those two sides. This angle is not included in those two marked sides. This angle is not included in those two marked sides. This order matters. Side angle side is a congruency property. Angle side side is not. I have to have the angle included. If I know any two angles in one of the sides, so if I know angle side angle, then I'm good. If I know all three sides, I'm fine. I know that the two triangles are congruent. A triangle that is not a right triangle is called an oblique triangle. The measures of three sides and three angles of a triangle can be found if I know at least one side. I can know two sides or three sides, and any other two measures. So if I know at least one side and two other measures, so either I need to know either all three sides, one side and two angles, or two sides and the included angles. If I know those things, then I can solve the triangle. So here are my four cases. I'm not quite sure why it puts them in this order because we're going to talk about cases 1, 3, and 4 before we talk about case 2. Case 2 is what we call our ambiguous case because it's a little wishy-washy. So for case 1, I know one side and two angles. That case is either side angle angle or angle side angle. I can term it either of these two things. It doesn't matter. Now, guys, here's the tip. Because if I know two angles, I know the third angle. Think this through. If I have a triangle, and let's say I know this angle is 50 degrees and this angle is 70 degrees, those are the two angles I know. What measure does this third angle have to be? Well, if this is 50 and this is 70, that adds up to 120, and we know the sum of the angles in a triangle is 180, so this one has to be 60 degrees. Anytime I know two angles, I know the third. All right, my ambiguous case. This is the one that I told you we're not going to get to right off the bat, but we'll talk about it for a minute. If I know two sides and one angle that is not included between those two sides, I usually say SSA as this case. The book sometimes says ASS, which is kind of fitting because this case is a pain. If that angle I know is not included between the two sides, this is my ambiguous case because it might lead to one triangle, but it might lead to two triangles, or there may not be any triangles formed. We just don't know. This case we tackle last. We're going to talk about cases 1, 3, and 4 first. Case 3 is where we know two sides and that angle that is included between the two sides. This one is side angle side. That one's fine. That one doesn't give us any trouble. And then case 4, is when I know all three side measurements. Side, side, side. Notice that we didn't talk about what happens if we know the three angle measurements. Let's say that we have, for example, an equilateral triangle. Well, an equilateral triangle is also going to be an equiangular triangle. If I have an equiangular triangle, my angle measures are all 60 degrees. Well, I can sketch that equiangular triangle like this, or I can sketch it like this, or you know what? I could get significantly smaller or significantly larger. The angle measures are all the same, so the shape is the same, but the size is not the same. I say that if I know all three angles, I know that the triangles are similar, but I don't know that they're congruent. I have no guarantee because I don't know how far apart the angles are. Okay, let's move forward and talk about deriving our law of sines. Now we have an investigation packet that if we're able to meet together, we work through that investigation packet. Since we're not able to meet together, we're going to talk through this page of the notes instead. To derive the law of sines, we're going to start with an oblique triangle, such as this acute triangle or this obtuse triangle. Now we can work through with both of them because it gives us the same thing. These are both oblique. It does not have a right angle. But I can find the altitude or the height of the triangle by forming that right angle. You see that is the height h of each of these triangles. The altitude for an acute triangle is inside the triangle. The altitude for an obtuse triangle is outside the triangle. That doesn't matter. This discussion applies to both. First, I'm going to construct that perpendicular from B to the opposite side AC. That's this height, this altitude. Let h be the length of the perpendicular. That means that C, right here, this side C in either triangle, is the hypotenuse of that right triangle that was formed when I made that altitude, that perpendicular h. And that means A is the hypotenuse of the other right triangle that is formed. Hopefully you can see that in both of those, the acute and obtuse, I have formed two right triangles. For the acute, I have formed two right triangles that are both part of the oblique. For the obtuse, I have this small right triangle here, and then I have the larger right triangle there. For triangle ADB, the smaller one in both, sine of A, remember sine is opposite over hypotenuse. Sine of A is going to be h over c. For both of these, sine of A is h over c. Or h, if I solve for h here, I multiply by c. So that would be c times sine of angle A. Now look at the other triangle. Right here, BDC, BDC, the big one right there. What if I look at sine of angle C? Well, sine of angle C is opposite over hypotenuse, h over A. For angle C here, it is still opposite over hypotenuse, h over A. Or again, if I solve for h, this time I have A times sine of angle C. Notice that I label my sides with lowercase letters and my angles with capital letters. The side is labeled by the name of the angle it is opposite. So side A is opposite angle A, side C is opposite angle C. Also notice that the longest side is opposite the largest angle, and the shortest side is opposite the smallest angle, which leaves, of course, the medium side to be opposite the medium-sized angle. Okay, back to our derivation of the law of sines. We have these two statements that are both true for any triangle, acute or obtuse. Since h is equal to c times the sine of A, and h is also equal to A times the sine of C, then we can set these two expressions equal to each other so that we have A sine of C is equal to C sine of A. That is a true statement. Those two things are equal to each other because they're both equal to h. So I can rearrange some things. I can divide by the sine. So if I divide by sine of A, that moves that over there. And if I divide by sine C, that moves that over here. So that I get A over sine A is equal to C over sine C. Now I could extend this by constructing altitudes, perpendiculars from another vertex, and find the values for angle B, side B as well. And what I get to is the fact that I have a ratio that is always true. For any oblique triangle, I can write my ratios comparing the length of the side to the sine of the angle like this, so that side A over sine of angle A is equal to side B over sine of angle B is equal to side C over sine of angle C. Because of the way the construction happens, if I have congruent triangles, this is always going to work. This is the law of sines. The lengths of the side are proportional to the sines of the measures of the angle opposite them. Now, one thing, I can't adjust these quite the way I like, so it's a little awkward, so we have to switch to the next page. It doesn't matter which direction I write my law of sines in. I can put the side lengths in the numerator, or I can switch that and put the angle, the sine of the angle, in the numerator. It truly does not make any difference which way you write it. You write it the way that is easiest to find your unknown. It's good to put the unknown, whatever I'm solving for, in the numerator, just because it makes it arithmetically a little simpler to solve. Okay, so let's start solving some triangles. For this first example, we're going to apply the law of sines. We know side, angle, angle, because the information I'm given about my triangle is the measure of two angles and one side. Now, the very first thing that I need to do every time I start one of these problems is to sketch my triangle. It's an oblique triangle. It doesn't matter exactly what shape it is. I'm going to label it A, B, and C. Angles have capital letters. Sides have lowercase letters. Side A is opposite angle A. Side B is opposite angle B. Side C is opposite angle C. And then I'm going to fill in what I know. Well, I know that angle A is 28.8 degrees. And I know that angle C is 102.6 degrees. And I know that side C is 25.3 inches. Those are the three pieces of information that I have. I need to solve for the other three. I'm going to solve for angle B, and side A. Well, that third angle is always super easy to find because I know that the sum of the three angles in a triangle is 180 degrees. So to find angle B, I'm going to add up my other two angles and subtract that value from 180. So I've got 180 degrees minus that 28.8 minus the 102.6 gives me my measure of angle B as 48.6 degrees. And then I'm going to go back and I'm going to find my two missing side measures. Well, I know one ratio. I know both the measure of angle C and I know the length of side C. So that is what I'm going to use. Remember that we always use our knowns every single time that we can. So I'm going to I need to find the measures of these two sides. I'm going to set 25.3 inches over the sine of 102.6 degrees because I know side C and angle C. And then I'm going to solve for, and it doesn't matter which one I solve for first. Let's go ahead and do A because A comes before B in the alphabet. I'm going to solve for side A. Side A is opposite angle A. So I set up my law of sines like this. Side C opposite angle C, side A opposite angle A, and then I use a proportion to solve for my missing value. When I'm solving proportions, I use cross products. I multiply the numerator of one side times the denominator of the other, and I set them equal to each other. I'm solving for A, so really all I have to do is multiply this other side times sine of 28.8 degrees. What I have, if I go ahead and work through using my cross products, I get 102.6 degrees times side A equals 25.3 degrees. Not degrees, 25.3 times the sine of 28.8 degrees. So to finish solving for A, that's my A that I'm solving for. To finish solving for A, I'm dividing both sides by the sine of 102.6 degrees. Okay, so A is equal to this. That's what I plug into my calculator. So, find my calculator. It does not. It does matter. Excuse me. It does matter what mode I'm in. I'm using degrees, so I need to be in degree mode. So I'm going to change to degree mode first. And in degree mode, I'm going to do 25.3 times the sine in degree mode of 28.8 degrees, enter. And then I'm going to divide that by the sine of 102.6 degrees, enter. And I get this value of 12 and then several decimals after. I'm going to keep my significant digits. I've got 3 significant digits in this problem, so I'm going to round to 3 significant digits, which means side A is 12.5 inches long. Make sure you use your units as well. Okay, now I'm going to go back and I'm going to solve for sine B, because that's my last missing value is side B. I'm going to start with my known, 25.3 over sine of 102.6 degrees. That's my known ratio. I'm solving for side B. That's going to be over the sine of angle B that we've discovered is 48.6 degrees. So when I solve for this, B is going to be, when I'm solving using my cross products, I have 25.3 times the sine of 48.6 degrees divided by this time the sine of 102.6 degrees. I set it up using cross product, so I know I'm multiplying these two together, and then I multiply the sine of 102.6 by B, which means to solve for B, I have to divide by that value. When I plug this into my calculator and round it to 3 significant digits, I find out that side B is 19.4 inches long. Okay, we've got several more examples of these where I'm solving using the law of sines. Remember that the very first thing you do every single time is going to be to sketch your triangle. And it doesn't matter what your triangle looks like. It doesn't matter where you start labeling A, B, C. Make sure that you label correctly though. I'm given angle A is 32 degrees. I'm given angle B is 81.8 degrees. And I'm given side A, which has to be opposite angle A, is 42.9 centimeters. I need to solve for side C and for side B and for angle C. Always do that angle first. That's going to be the easiest thing. So angle C is going to be 180 minus the given angles, those degree values that I've already used. So it comes out that angle C is 66.2 degrees. And then I'm going to go ahead and solve for side C and side B. It doesn't matter which comes first. If we do side C, we know that 42.9 is the length of side A. Measure of angle A is 32 degrees. If we're solving for side C, we put that over sine of angle C. When you set that up as a proportion, find your cross products to solve, you're going to get a measurement for side C as 74.1 centimeters. Don't forget your units. And then that third side that you still don't know is side B. I'm going to start with my knowns, and I'm going to set that equal to B over the sine of angle B. And when I solve using proportion, my cross product, I find that side B is 80.1 centimeters rounded to 3 significant digits. All right, that's the basics of using my law of sines, especially when I know 2 angles and 1 side. So angle, angle, side, or angle, side, angle as my congruency property. Same application, same 3 pieces of information, but now we're applying it to a problem that is a realistic problem someone might have to solve. What am I doing? 32.5 over 40, I do.